Hi everyone, this is a presentation on factors, multiples and primes. We've got a few images on the first slide, it's just a bit of fun really, but we've got Euclid there, the Greek mathematician responsible for first proving that primes were infinite in nature. We've got the largest prime discovered to date, which is 2 to the power of 57,885,161, subtract 1. Clearly you need to subtract 1 or it will be divisible by 2. But yeah, that's the largest prime discovered to date, and right next to that we've got Curtis Cooper, who was the mathematician responsible for discovering it. Now naturally these kind of discoveries are all done with computers nowadays. We expect that current biggest prime will be broken in the next year or two. If you look on Wikipedia, you'll see that these records for largest primes are smashed all the time, and there's actually a lot of money for it. Curtis Cooper himself, I think he was awarded $50,000 or $100,000 for finding that prime number, so there's some serious money involved in this business. Anyway, let's get on with the presentation. Let me just remind you about factors and multiples first. Now, I'm certain that you'll remember many of these ideas, but it never hurts to quickly recap, but I will go through this very, very quickly. Firstly, a multiple of a number x is an integer formed by multiplying that number x by another positive integer. So this is best seen really for students with examples. They're not going to get it from a sentence like that. It's best to give an example. So for example, 60 is a multiple of 5 because 5 times 12 is 60. In fact, you could say that 60 is the 12th multiple of 5. In that way, in that sense, students will most often associate multiples with numbers in a numbers times table. So anything in the 5 times table is a multiple of 5. Anything in the 7 times table is a multiple of 7. And that's a very sensible way of looking at it. Likewise, factors. Well, factors are obviously the opposite of multiples, but a factor of a number y is an integer that may be multiplied by some other integer to produce y. Hence 8 is a factor of 24 because 8 times 3 equals 24. Another word for factor, by the way, is divisor. You might come across that word. I actually almost prefer that word, but factor is more commonly used in the exam. Note that factors are often given in pairs for obvious reasons. If I'm going to, for example, a fairly typical GCSE question is list all the factors of 20. Well, if you're going to list all the factors of 20, why not say, okay, we've got 1 and 20, we've got 2 and 10, and we've got 4 and 5. The easiest way to do it is to list them in pairs. Finally, it's worth just noting, as I just mentioned, that factors and multiples are the opposites of one another. 5 is a factor of 60 if and only if 60 is a multiple of 5. Now, just a quick couple of questions I'm going to let you dwell on. You might want to pause the video here. Can you tell me what types of numbers have an odd number of factors? Only a very special type of numbers has an odd number of factors. What is that subset of numbers that have an odd number of factors? Okay, I hope you've come up with the answer. It is, of course, the square numbers. The square numbers have an odd number of factors because one of their factors is repeated twice when you do the factor pair. So, for example, 16, which is clearly a square number, is, well, let's have a look at its factors. We've got 1 and 16, we've got 2 and 8, and then we've got 4 and 4. But you don't repeat the factor there, hence it's got an odd number of factors, 5 factors. Right, okay, so let's move on now and let's look at primes. Primes are much more interesting, to be honest, than factors and multiples. I mean, that's not to say factors and multiples aren't extremely useful, but primes, I really enjoy teaching primes, to be honest. It's good fun. So, yeah, let's have a look at this first quote, which is actually from a very famous recent novel called The Curious Incident of the Dog in the Night Time, which I haven't read, personally, but I'm aware of the fact that it's about an autistic boy who is very keen on numbers, and he famously remarks in the novel that prime numbers are what is left when you've taken all the patterns away. And what a marvellous description of prime numbers that is. There are naturally other descriptions which have been given. Another one is Marcus de Sautoy famously described them as the atoms of arithmetic. Actually, he may not have been the first to have said that, but yeah, they are essentially new numbers, numbers which are new to the number system. Now, they have precisely 2 factors, one in themselves. In some sense, they are new numbers, hence the word prime, as they are not a repetition of any other number. Another way of looking at it is seeing them as the atoms of arithmetic, as just mentioned. Now, what I always like to do when I mention prime numbers, perhaps for the first time to year 7, although quite often they've heard of them before, is I like to write them on the board and challenge them to find a pattern, because I always tell them before they try and find a pattern that, oh, this has never been discovered before, any kind of pattern to the prime numbers. I mentioned the fact that it's worth an incredible sum of money if they do find a pattern to the primes, and then I let them sort of struggle a little bit and see what they come up with. It's always amusing because there's always someone in the class who seems to believe that they've suddenly found a pattern to the primes, even though you've just told them that people have been looking for this pattern for thousands of years and no one's found it. It's remarkable how optimistic young people really are. But yeah, I hope you will challenge your own classes to that and see if they enjoy the challenge. Okay, so we're going to be looking at a proof of the primes very shortly, but firstly let's have a look at something which is really important and certainly a big part of the GCSE. It's the fundamental theorem of arithmetic. Now this is what the scheme of work meant when it mentioned the unique factorisation theorem. Now this fundamental theorem of arithmetic simply says that every single number, positive integer obviously, not fractional numbers or anything like that, but every single whole number is uniquely expressible as a product of its prime divisors or its prime factors, or it must be prime. Now that is an astonishing fact. I find it astonishing anyway, because any number you can think of any old even number really, and then just start decomposing it into its product of prime factors, and you will have a unique signature, if you like, for that number. That's a fantastic property, very, very useful to many a mathematician. Now, I'm going to have a look at a couple of methods of writing a number as a product of prime factors. Essentially, they're the same method, but let's have a look at the first one anyway. The first one is where we write out the number 300. First thing we do is we try and look for the first prime number which divides into 300, which is naturally 2. Always try and halve it first, and that gives us 2 times 150. Now look at 150. Can you halve that? Clearly you can. You can write it as 75, so we've got 300 is 2 times 2 times 75. Now clearly 75 is odd, so it can't be halved. So now try and divide the next prime number into it. Fortunately we can. 75 is divisible by 3, so we can write it as 2 times 2 times 3 times 25. And finally, now students often ask, when do you stop? 25 still isn't prime, so we still try and decompose it into its prime factors. 25 can be written as 5 times 5, and so now we can see that 300 is in fact 2 times 2 times 3 times 5 times 5. Now, what the fundamental theorem of arithmetic is saying is that there's no other way of multiplying primes together and getting 300. There is only one way of doing that, and that is the way in front of you. Now the question will often ask you to write it in index form, and that's what I've done in the final line. It's a very powerful theorem, this. It really is. And if your school ever does the Maths Challenge, the United Kingdom Mathematics Trust Challenge, the UKMT Challenge, they will have lots of questions actually where that theorem can be very, very, very useful. So bear that in mind. Okay, and to the right of that I've written 252 as a product of its prime factors, but this uses a tree, and it's actually the method I prefer, but not for any good reason, to be honest with you, other than the fact that it was the way I was always taught to do it. Here we can see that 252 is 2 squared times 3 squared times 7. It can be a little bit confusing, the tree method, for students, because what they can sometimes do is introduce a non-prime number into their product at the end. So be warned about that method, but I must admit I actually prefer it. So it's funny the way we are with these kind of things. But yeah, I'm sure you can see that essentially we're doing exactly the same thing either side. Bear this in mind, because this is what the question is asking for if it ever asks you to express a number as its product of prime factors. Now, I'd just like to take a moment to discuss why primes are important and interesting, because certainly students will quite rightly ask why primes are so important to mathematicians. And, well, firstly I'd say to mathematicians they're always going to be really important, because there's so many unsolved problems which exist in the field of prime numbers. Firstly, whether anybody can spot a pattern would be pretty nice, although most mathematicians are fairly convinced there is no pattern. But secondly, there's a famous conjecture called the twin prime conjecture. Now, a twin prime is just 2 prime numbers which have a difference of 2. So 17 and 19, or 3 and 5, are twin primes. Now, there's a famous conjecture that there are infinitely many twin primes. but it's never ever been proven either to be true or false. So we still don't know the answer to that one, but once again, it's one of those things you can challenge students with, although they're unlikely to become to get anywhere near to the answer, but sometimes it's worth mentioning. Outside of that, its practical uses are essentially mainly in cryptography. The most famous example being the RSA algorithm, although there's also Diffie-Hellman key exchange. Now, all of the encryption on the internet pretty much, and I'm certain that most students will be using internet banking or use passwords on Facebook or use HTTPS websites. Well, all of those things depend on encryption, and a hell of a lot of encryption uses prime numbers. So yeah, prime's very useful if you want to get into code breaking or anything like that. I'm also told that primes are used in harmonics and also when constructing microwave ovens. There are actually lots of funny little uses they find for primes. And the last thing I want to say is sequences of numbers that don't conform to any observable pattern are actually really rare. Yeah, there's a formula which exists which tells you how many prime numbers, well, an upper bound for the number of prime numbers in a certain up to a certain number. So the number of prime numbers you're going to find from 1 to 1,000 or 1 to 10,000 or 1 to 100,000, but there's no formula predicting where the primes will occur. And that kind of randomness is really important to mathematicians, especially you can see why it's important in cryptography, because generating randomness, pseudo-random number generators, that kind of thing, very useful for protecting your data, for protecting codes, for keys and that kind of thing, because they don't want you to be able to predict things in cryptography. That's the idea of uncrackable codes. Anyway, let's move on to the proof that there are an infinite number of primes. Now, this is not part of the course. It's certainly something I'm just showing you to enrich your understanding of prime numbers, but it's a lovely proof. Proof is becoming more and more important in GCSE and A-level. I very much would be surprised to see this at GCSE or A-level, because it's a standard proof which you could teach someone. Maybe it will turn up at A-level, but it's nice for them to see it, because why not teach them things which lie beyond the scope of the syllabus? It will be useful for their reasoning. It really will. So, first I want to say, well, why should there be an infinite number of primes? Because if you think about it, prime numbers are numbers which have no other number dividing them. Why can't we get to a certain point of a certain size of number where there's bound to be another number which divides into it? Let's say we're past billions, trillions, gazillions, and all of a sudden we're at a point where you can always find that numbers are divisible by 4 or 5 or 10 or 15 or 20. That seems on the surface of it that it might be true, that there might be a greatest prime number. Well, that's not the case, because Euclid has offered a proof which is a really good example of something called proof by contradiction, which you may have heard of before. It's sometimes called reductio ad absurdum in Latin, if you like to show off with a bit of Latin. But yeah, it's a proof where you start by assuming the opposite and then go on to show that it leads to an absurdity. So that's exactly what we're going to do here. We're going to assume that there is a greatest prime number, and we're going to call that number P. Now, this is what Euclid did, and it is genius. It really is. He said, well, if there is a greatest prime number called P, let's consider the number x, where x is 2 times 3 times 5 times 7 times all the prime numbers just once, up to and including this number P. And then add 1 to it, and that is this number x. And then ask yourself, is this number prime? Well, surely this number must be prime, since every single number you try and divide into it will have a remainder of 1. Now, why is that? And this is the subtle bit. Well, if the unique factorization theorem holds, then every single number you divide into it can be expressed as a product of its prime factors. In other words, when you're dividing x by, say, 16, you're really just dividing it by 2 times 2 times 2 times 2, which clearly will give you a remainder of 1, because it's 1 more than an even number. Yeah? And the same holds for any other number you try and divide it by. Hence, x must be prime. Now, that's an astounding result, because if x is prime, well, hang on a second, we said P was the greatest prime number, and yet x is clearly much larger than P and prime. Now, that completely goes against our original assumption that p was prime, and that p was the greatest prime, and therefore the only other option is that there is no greatest prime number. Therefore the idea that there is a greatest prime number must be false. I really like that proof, and I hope you enjoyed it. Okay, there's just a couple more things I wanted to cover in this video. The first thing is highest common factors and lowest common multiples. Now, they can actually cause some trouble for students when they try and find those. They're really not that bad though. I mean, it should be easy enough to understand. One of the common things I hear is lowest common factors and highest common multiples. You hear that all the time from students, trust me, and you have to explain, look, the lowest common factor for any two numbers is 1, and the highest common multiple is infinitely large, so they would be meaningless. But yeah, sometimes students can get a bit confused as to how to find the HCF, as I'm now going to call it, and LCM of any two numbers. Well, I really want to show you this method with Venn diagrams, because it makes the whole process so simple. So how do we do it? Well, okay, if we just draw a Venn diagram out and we include all the factors, prime factors that is, of 18 and all prime factors of 120, and on the overlap of the Venn diagram, the intersection that is, we're going to include the prime factors which they both share, yeah? So they both share a 2 and a 3, but 18 has an extra 3 which can go on its side outside the intersection. 120 has 2 more 2's and 1 5 which can go outside of the intersection. Yeah. Well, the intersection of the two sets, 2 times 3, which is 6, is the highest common factor. It just gives you the highest common factor straight away. And the union of those two sets, that's 2 times 3 times 3 times 2 times 2 times 5. If we multiply all of those prime factors together, we're going to get the lowest common multiple. And when I show that to my students, especially if they haven't seen it before, they always say, does that always work? And the answer is yes, that always works. So just encourage your students, if they've ever got to find HCF and LCM, write out the prime factor decomposition of the two numbers you're looking at, draw a quick Venn diagram, and the answer is obvious. Hope that's been useful for you. Okay, so next we're looking at recurring decimals. Now I'm not going to talk to you any longer because I've got a little video prepared for you for this, but yeah, on the video you will see how to convert a particularly awkward recurring decimal to a fraction. I hope it's very useful. I hope this session's been useful. All the best, and I'll speak to you soon. Hi guys, I'm just going to show you very briefly how we convert recurring decimals into fractions. Now I'm sure you remember this, but I just wanted to show you a particularly awkward kind of one, just so you don't get caught out when you're doing it, just so you remind yourself how it's done. Let's say we've got to convert the number 1.0812812 on into a fraction. It's pretty horrific, and it's about as nasty as they'll ever make it, at least on the Excel syllabus. I've never seen it actually on any syllabus any more difficult than this, and they can't really make it any more difficult than this really. I mean, it would take too long to do the question, and it would be time probably more valuably spent on other aspects of the syllabus. So what are we going to do with this? Well, the important thing is we need the same decimal expansion, the same recurring figures after the decimal point. Maybe that's the best way of putting it. So what I'm going to do is I'm going to multiply this first by 10, moving the decimal point 1 to the right. And I'm going to write it like that, just to remind myself that this is a recurring decimal. Now, I really need to multiply it by another 1,000, because what I really want is exactly the same figures. Oh, messed that up there. Let's just go over that like that. Sorry, that looks so horrible. Okay, because I really want the same figures appearing after the decimal point, yeah? Dot, 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 dot. Now I've times that previous one by, well, the decimal place has moved 3 places, so I've times that by 1,000, so that's going to give me 10,000x. See, now I'm fortunate, because when I subtract these, the 0.812812 is going to disappear, yeah? And that's the key thing. Now, some of my students don't immediately see this, and so, you know, they probably don't immediately see that I needed to times it by 10,010. I sometimes get them to write out x, 10x, 100x, 1,000x, and 10,000x until they see which ones have the same figures appearing after the decimal point, because then they're absolutely fine. Now, obviously, we subtract. Now let's not forget either, I've forgotten it in the past, to take away not just the 0.812s which disappear, but also the 10 from 812, leaving 802. And that is clearly 10,000 minus 10, which is 9,990x. Now obviously I can write my answer down, so it's x is 10,802 over 9,990, and I might want to simplify that, 5,401 over 4,995. And that's all there is to it, really. I don't think I've made a mistake in my working. I always like to check over it afterwards. It's a good bit of advice to give yourself and any students after you do a bit of maths. Let's face it, it's very easy to make little careless errors. It's almost impossible to avoid. So yeah, that's converting really awkward recurring decimals into fractions. I hope you enjoyed it. I hope it's made things clear for you. And I will be speaking to you soon, I'm sure. Okay, bye-bye.